Okay, so let's start our today. So, uh, uh, okay, so, okay, so we pick any point, around the lattice point, and then, what we do that, um, yeah, so maybe let's draw some picture first. So, so this is a point A here, and then so it is other than the lattice point and also the origin. So maybe I'll use letter this lattice point union the origin. Maybe I'll use this union the origin, and also yeah. So maybe yeah. So maybe I think it's better. It's better. So, and then what I do is that I so yeah, so then I draw the parallelogram, right? So here it is the parallelogram. So a plus omega 1, and then a plus omega 1 plus omega 2, and then so this one is a plus omega 2, and then this is that. Okay, so now okay, so now when we integrate over this boundary, okay, so let's give an orientation for this one, right? So, so first I go from a to a plus omega 1, and then I go from a plus omega 1 to a plus omega 1 plus omega 2, and then so on and so forth. The integral is evaluated by adding the contributions from opposite side of the parallelogram, and then we obtain the equation. Okay. 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 Yeah. So so by the residue theorem, right? So okay. So so now by the residue theorem. Wait, hold on 1 second. Okay. By the residue theorem. So by the residue theorem, so what we have is that okay, so I want to use the residue theorem, right? So I want to use the residue theorem, but yeah. So the question is that okay, yeah. So we know that this zeta, right? So we by just what we derived earlier. So this zeta is a holomorphic function on this lattice point union 0. Okay. Oh yeah, so this is a dot equal to 0. Okay, yeah. So by this you already set. Okay, and then so and then what we have is that yeah, so it's so this is part homotopy to the constant loop. Yeah, we proved before, and then yes, so then we have that. Let's use so we have the 1 over 2 pi I of the integral over the parallelogram, right? Zeta z dz, right? Oops. it z dz. So this is equal to okay. So we know that this f is holomorphic. The zeta is holomorphic. So because yeah, so this parallelogram, right? So contains at least one lattice point. Okay, so why it contains why it contains exactly one lattice point? Let me see. So why it contains so let's see. So yeah, so if it contains two different lattice points, then they must differ by at least one copies of omega 1 or one copies of omega 2, right? And then this implies that yeah, so they differ by one omega 1 or one omega 2, and then it means that their difference, their difference is equal to like some copies of omega 1 or omega 2, right? But if I take any point on this parallelogram, their difference. So I can So if I take any point on the parallelogram, I rewrite it as like some multiple like c times omega 1 plus d times omega 2, where cd is just some like numbers, like some number between between sorry, it will be like so let me say this. So maybe I think I want to keep this one. So so let me do this. So okay. Okay, so y PA contains exactly one lattice point. Okay, so PA is equal to, instead of all, like let's say C omega 1. No. So start with the point A, right? So A plus C1, not C1, just C, okay. So C omega 1. plus d omega 2, right? Where c d is just in close interval 0 to 1, right? So yeah, so we can define PA to be this one, right? If CD both equal to 1, then just A plus omega 1 plus omega 2, and then CD between 0 and 1 just expand out, okay? And then, so then, if I take any, like, so let's suppose for in contradiction that there are like a two lines point, right? So, yeah, so if if two, let's say that so if by contradiction, right? So so if there exists like 2 points, like let's say A1 A2, right? In PA intersect this lattice point, let's say including 0, okay? Because yeah, including 0, and then the A1 minus A2, right? So it is equal to some numbers, let's say N1 omega 1 plus N2 omega 2, where these N1 comma N2s are not just 0, 0, right? And also integers, right? I don't bother write down the integer sign. I just don't want to write down the integer sign. Okay, and then so this means that yeah. So then you can just discuss the situation, right? So if like N1 N2 they are like integers, and then if N1 equal to so yeah, so let's just say that N2 now equal to 0, right? So assume with all loss of generality that N2 equal to 0, and then if N2 equal to 0, so assume without loss of generality that N2 is not equal to 0. So yeah, so then we have that A1 minus A2 is equal to let's see, so okay, so let's say that. So let me come out some letters. So suppose, okay, then suppose A1 is equal to x1 omega 1. Sorry, A1 is equal to A plus, yeah, let me just A plus x1 omega 1 plus y1 omega 2. And then A2 is equal to A plus x2 omega 1 plus y2 omega 2. Okay, so then we have that. So then this relation, right? Then we have so after taking the difference, y1 minus y2. Okay. So we know that these y1 y2s are between 0 and 1, right? So I just so x1 x2 y1, y2, they're all between like 0 and 1. Okay. So but then we have that y1, y2 is equal to some integer. Some n2, right? So so the only possibility that basically you have two integers. Yeah, so the only possibility is that so this implies so y1 minus y2 equal to n2 implies that so how can I write this? So n2 is non-zero, right? N2 is non-zero. So so yeah, so if let's say that, so if n2 is equal to 2, then this cannot happen, right? So because y1 is equal to y2 plus 2. Yes, so which cannot happen, right? And then so then this implies that yeah, so this will happen if n2 is equal to either an integer that is bigger than or equal to 2 or less than or equal to -2, right? So then the only choice for n2 is that it's equal to 1 or -1, and then if it's equal to 1, then this is y1 minus y2 will be equal to 1. So 1 is 1, 1 is 0, right? And then so this yeah, so yeah, so and then yeah, so yeah, so and then if n2 is equal to 0, sorry, if n2 equal to -1, then we have the opposite, right? So then y1 is equal to y2 minus 1, then y2 is equal to 1, y1 is equal to 0. Okay, so yeah, so this implies that y1 comma y2 is equal to so either like 1 comma 0 or 0 comma 1. Yeah, so there's no other choice. Okay. So and then okay. Yeah. So and then what happened is that then whatever x, right? So because here we assume we call that generality that n2 is not equal to 0. So the situation where ny not equal to 0 is the same. Okay, so we first analyze n2, right? So then what happens is that so then if ny is not equal to 0, if ny is equal to 0, right? So then so these two are just the on the corner points, which is corresponds to the wait, shoot. Yeah, which is on the corner point, and then on the corner point means that this a must be less. This a must be on the lattice point, right? Because yeah. Because this y1, y2, they are exactly this LA2 they are supposed to be the lattice point. So there is a contradiction. And then what happens is that if x1, x2 is basically if these x1, x2s are let's see. So if these x1, x2 are also equal to positive -1, right? So then this would imply that the difference yeah, so if the difference of this x1 and x2 are also like this positive 1 or negative 1, just like the analysis that we did here, right? So this implies that this x1 comma x2 will also be like a 1 0 or 0 1. So that means that if that means that uh, yeah, so this gives all these so all these possible choices, they are all integers, right? So basically like this x1 x2, so based on our analysis, this x1 x2 y1 y2, they can only be integers, and then when they are integers, they just lies on the one of the corner points, right? So one of the corner points. So and then based on this analysis, this just says that one of the corner points are the lattice point. So not one of them, but just two these two are these two lattice points are on the corner. So this implies that this A is the lattice point. Yeah. So yeah. So this finished the proof. Okay. Then so yeah. So same then same analysis on N1. Let's see. So okay. So then let's see. So if N1 is equal to 0, then we have we have x1 equal to x2, right? Oh shoot. Wait, no. Wait. Okay. Okay, and then okay, and then yeah, I think maybe one better way to show that is okay. So maybe just follow this one. So then yeah, I think so. Then oh, okay. Okay, so I think maybe this is better. So, uh, so, uh, So since this A1, A2 they are the lattice point, so they are on the lattice point, so this implies that A1. So since this A1, A2, they are on the lattice point, union 0. So we have so A1 is equal to, let's say, N1 omega 1 plus M1 omega 2, and then A2 is equal to N2 omega 1 plus M2 omega 2. Okay, and then yeah. Yeah, so let's forget about this one. Okay. And then if we take the difference between this wait, so this A1, A2 they are on the lattice point, right? So then what happens is that, so they are on the lattice point. Then taking the difference, it should be integer. Yeah, I think I have to use the fact that they are on the integers. Okay, so so if I take the difference between this A1 and A2, N1 minus N2, wait. Okay. So so we have that wait. So A1 minus A2, okay, so which is equal to x1 minus x2 of omega 1 plus y1 minus y2 times omega 2, which is also equal to n1 minus n2 of omega 1 plus m1 minus m2 of omega 2. And then okay, so since Okay. So since we know that this I think by the linear algebra, right? So so omega 1, omega 2 is a basis that spans the whole C, right? If two wait. So this is the if I have two bases, if I have the basis, if I have omega 1, so if I have, let's say, if we have, so omega 1, omega 2 forms the basis of C, right? So, and then they are linearly independent, right? So therefore, I think it has a unique representation. So why, yeah, so these omega 1, omega 2, they are linearly independent. So this means what? So this means that okay. So linearly independent means that if you have a1 omega 1 plus a2 omega 2 equal to 0, right? Then this implies that a1 equal to 0 and a2 equal to 0. Okay. So yeah. So if you take the difference between these two, right? So this implies that x1 minus x2 minus this n1 minus n2 is equal to 0. So okay. So now since omega 1, omega 2 are linearly independent, so we have that x1 minus x2 is equal to n1 minus n2, and also we have y1 minus y2 is equal to m1 minus m2. Okay, and then yeah, so this will lead to the argument that so then this implies that let's say the first argument, so one implies that so x1 minus x2 is equal to 1 or -1, right? Shoot, it could be equal to 0. Okay, so or x1 minus x2 is equal to 0, or x1 minus x2 is equal to -1. Okay, and then yeah, so and then if it is equal to 1, then so this implies that yeah, so if x1 minus x2 is equal to 1, then I have that y1 minus y2 is equal to so then y1 minus y2 is equal to, it could be equal to 0, right? 1 or 0 or -1, right? Okay, so yeah, we can yeah, and then so this implies what? That what? So this implies that uh uh so if y1 minus y2 is also equal to 1, so this implies that okay. So oh shoot, I'm running out of space here. So let me just continue here. So if y1 minus y2 is also equal to 1, then because we have that x1 minus x2 is equal to 1, so we have that x1 must also equal to 1, x2 must also equal to 0, right? So and then y1 equal to 1, y2 equal to 0. And then what we have is that, yeah, I'm thinking of yeah. So if this x1 is not equal to 1, right? So then it must be less than 1. So if it's less than 1, then definitely it minus 1. It must be less than 0, which cannot happen. So yeah. So therefore therefore yeah, we have this relation, and then so then we have that this so then a1 is equal to a plus omega 1 plus omega 2, and then a2 is equal to a just a, right? And then so this yeah, so because x2 y2 is equal to 0, so and then this implies what? This implies that yeah, so this implies that yeah, so basically like yeah, so what we can say is that since this a2 is on the lattice point, right? So this implies that this a is in the lattice point, right? So which is a contradiction. Okay. Yeah. So yeah, I think like everything else, like so this is just one situation, right? So and then there's another situation that and similarly, right? So similarly, we can show all of them. The contradiction holds for every single case. So similar argument gives the contradiction for every single case. Okay. So yeah, so this implies that all the points are. So this implies that this contains exactly one lattice point. Okay. Okay. So now what I have is that okay. So now what happened is that because there is exactly one lattice point, so we have that is equal to the Wannian number of the lattice point. Okay, so that yeah. So what I showed is that actually it contains so that zeta not be the point in this the intersection. Let's say that it contains 0, right? So it could be 0. So wedge union 0 whole thing intersect this PA. So then, so this is equal to yeah. So here I think my argument shows that it contains no more than 2. That is point, right? So and then but I didn't show why it contains only 1 that is point, because I think it is obvious. Yeah, it is obvious that it contains only 1 lattice point. So and then so then it is equal to this Wannian number times the yeah. Okay, so let me think. So y contains only 1. Yeah, I think y contains only 1 lattice. Yeah, so y contains only 1 lattice point. Okay, so it's because yeah, so y contains okay, so okay, so y contains only 1 lattice point. So okay, so yeah, I think okay, so yeah, so let me think. So yeah, so why it contains yeah, so I think it has something to do with to do with A, right? Okay, so so y so PA intersect okay, so PA intersect this union of the lattice point and 0 is not empty. Okay, so if I show that it's not empty, then I show it cannot contains 2 different elements, right? So I just show that if there is a point a1 a2 a1 not equal to a2, right? And then this will lead to a contradiction. So yes, and then so here what happens is that if I have this one, and then if I show that it's not empty, then yeah, so it's the same thing as I show that yeah, so if I show that it's not empty, then yeah, if I show that it's not empty, then yeah, so it's just the singleton, it's just a singleton set, because yeah, so if there is another point b not equal to a, it belongs to that set. Wait, if there is another element b not equal to a belongs to the set, then there's a contradiction. Okay. Therefore, it is just the singleton set. Okay. Oh, because if okay. Okay, yeah. Okay, so yeah, so that's just because yeah, so they just show that. Okay, so so why this is yeah, so we can yeah, so let me just let me first just show you that first. Okay, let's show you that first. So uh so why not empty? So if it is an empty set, so what happens? So what happens if it is not the empty set? So if it is empty set, then if it is the empty set, okay, I think maybe it's better maybe if it's empty set, then okay, so why is empty? Okay, because a can be written, yeah, so basically I think so it's like the idea of remainder, right? So basically for this a, so its a can be written as some integer multiple of omega 1 plus omega 2, and then some remainders, right? And then after like adding and subtracting the remainders, after adding the remainders for the a, right? So okay. So so why can we? Okay, so maybe I want to say a lemma here. So let's say this. So a can be written as some, let's say, let's use the n1 n2 again. Okay, so n1 omega 1 plus n2 omega 2 plus something like the remainder, right? So c omega 1 plus d omega 2, where yeah, I think it's very obvious, right? So I think it's very obvious. So where yeah, so where n1 n1 n2 are integers, n1 n2 are the integers, and then c comma d, they are between like 0 1. Okay. Yeah. So yeah, I'll just leave it here. Okay. So I'll just leave it here. So yeah. So this is a singleton point. Okay. So this PA intersects the lattice point using 0, and then that. So yeah. So then that. Yeah. I just stopped showing this one. Okay. So and then that. Um. This zeta naught to be equal to be the unique element of this one, right? Okay. So basically, this is just the is equal to just this singleton set. Okay. And then this is equal to the Wally number of gamma, so which is the boundary so boundary PA comma zeta naught times the residue of the zeta naught of this zeta function. So then what is the Wally number? Okay. Okay, so I think yeah, because I have no time left today, so I think I have to stop here today. So yeah, so for the Wally number is I think there is a past homotopic property that you have the parallelogram, and then yeah, so I'll continue next time for the Wally number property. Okay. Okay. See you.